question and intrigue. What if everything you thought you knew about reality was just a cosmic whisper? Have you ever wondered about the truly inexplicable, the things that make black holes seem mundane? Join us as we journey into the universe's most bizarre corners, where the unimaginable isn't just a concept, it's a phenomenon. Look at this. This is us, our home, the pale blue dot. For generations, this image, whether seen from the Moon, from Voyager 1 at the edge of our solar system, or from the International Space Station, has captivated us. It's a breathtaking symbol of life, fragility, and our shared humanity. It grounds us, it makes sense, it looks hospitable. And for most of human history, it was the only picture we had of a world. A planet. A place where things happen, where life thrives. But what if I told you this familiar, comforting image, this blue marble, is one of the most misleading photographs ever taken when it comes to understanding the rest of the universe? What if our Earth, with its gentle spin, its predictable seasons, its life-giving sun, is not the template, but the exception? What if the cosmos is a realm of such profound, mind-bending strangeness that our everyday intuition is not just unhelpful, but actively prevents us from seeing the truth? We tend to think of space as, well, empty. A vast, silent vacuum punctuated by distant points of light. We imagine planets neatly orbiting stars, much like ours. We conceive of stars as stable, predictable furnaces. And black holes, just cosmic vacuum cleaners, right? But these easy analogies, these comforting mental models, are about as accurate as drawing a map of the world based only on your backyard. The universe is not just bigger than we imagine, it's different. Fundamentally, bewilderingly different. Think about it. We live on a world where water freezes at 0 degrees Celsius and boils at 100, where gravity pulls us gently to the surface, where a year is 365 days and a day is 24 hours. These are the parameters of our existence, the bedrock of our understanding. Yet, out there, beyond the delicate bubble of our atmosphere, beyond the familiar orbits of our planetary neighbors, none of these rules hold sway. Consider the simple act of looking up at the night sky. We see stars, millions of them. But what if a significant portion of the planets out there don't orbit stars at all? Imagine worlds adrift in the infinite blackness between galaxies, never warmed by a sun, yet potentially teeming with subsurface oceans, kept liquid by internal geothermal heat. Worlds that have been ejected from their birthplaces by some cosmic slingshot, forever condemned to wander alone. According to recent research and simulations, these rogue planets might outnumber starbound planets by a significant margin. They challenge our very definition of what a planet is, and more importantly, where life might arise. No star, no warmth, no light. We've always been taught life needs a sun. But perhaps that's just another terrestrial bias. Or take the concept of a year and a day. Our Earth spins and orbits at a comfortable pace. But what about a planet that never turns? One side locked in eternal scorching day, the other in perpetual freezing night. Only a narrow band, a terminator zone, experiences anything akin to twilight. Imagine the atmospheric chaos. Winds whipping across the entire planet as the superheated air from the day side battles the frozen air of the night. Scientists have found many exoplanets in such tidally locked states, challenging our notions of climate, weather, and yes, even habitability. Could life exist there? Not as we know it perhaps, but life adapts, and the universe is full of adaptations we haven't even dreamed of. Our common misconceptions often stem from a lack of scale, but also a lack of imagination rooted in scientific possibility. We think of atoms as tiny, fundamental particles. But what if you could crush a star so intensely that its atoms cease to exist, where protons and neutrons themselves are compressed into a sea of their constituent quarks, forming something beyond a neutron star, something that, frankly, sounds like it belongs in science fiction, a quark star. The theoretical physics is mind-bending, but the universe is under no obligation to be intuitively sensible. And what about the emptiness of space? We learn about gravity, but we don't often truly grasp its tyrannical, shaping power across cosmic distances. It's not just holding us to Earth, it's bending light from distant galaxies, creating cosmic mirages. It's weaving a vast, invisible web of dark matters that underpins the entire structure of the universe, binding galaxies together like an unseen scaffolding. We can't see this dark matter. It doesn't interact with light, but we can feel its presence. According to decades of observation, from galaxy rotation curves to gravitational lensing, this invisible stuff makes up about 27% of the universe, far more than the ordinary matter we're made of. And yet, we still don't know what it is. Then there's the truly bizarre. The universe isn't just full of things, it's actively doing things that defy our everyday understanding. It's expanding. Not just expanding, but accelerating in its expansion, propelled by an even more mysterious force called dark energy, which makes up a staggering 68% of the cosmos. This isn't just empty space getting bigger, it's space itself being stretched, pulling galaxies apart and threatening to eventually plunge the universe into a cold, lonely, dark future. This mind-boggling phenomenon was only discovered in the late 1990s, completely upending our prior models of the universe. So, when we embark on this journey, I want you to set aside your blue marble. Set aside the comfortable, predictable, and, frankly, rather tame universe you think you know. We're going to dive deep into the truly bizarre, the perplexing paradoxes, and the astonishing realities that scientific discovery has unveiled far beyond our home planet. We'll unravel common misconceptions about phenomena you thought you understood. We'll introduce new theories and insights from the cutting edge of astrophysics, cosmology, and planetary science. And we'll explore the counterintuitive conclusions that emerge when we bravely face the weirdness of the cosmos head-on. From rogue planets wandering the interstellar void to diamond worlds where the mountains themselves are gems, from stars that refuse to die to objects so dense they challenge the very fabric of matter, from supermassive black holes that shape entire galaxies to ripples in space-time itself, we're going to explore the ultimate cosmic oddities. We'll ask why they exist, what they tell us about the fundamental laws of nature, and how they force us to rethink everything we thought we knew. Are you ready to truly see the universe? Are you prepared to have your preconceptions shattered and your sense of wonder reignited by the cosmic strange? Because the truth is, the cosmos isn't just stranger than you imagine, it's stranger than you can imagine. And our journey into its most profound oddities begins now, with a look at the cosmic wanderers that defy stellar companionship. Now, let's take that intuition and stretch it to its breaking point. When you hear the word planet, what comes to mind? Probably something like Earth, or Jupiter, or even Mars. A world, often rocky or gaseous, that gracefully circles a star, bathed in its light and warmth. This is the model we've ingrained, the cosmic blueprint. But what if I told you that a substantial, perhaps even dominant, population of planets in our galaxy exists in perpetual, unyielding darkness, adrift in the vast, cold emptiness between stars? No sun to call their own, no solar system to anchor them. These are the rogue planets, the cosmic orphans, wanderers without a sun. It sounds like pure science fiction, doesn't it? A planet without a star? How could such a thing even form, let alone survive? Our understanding of planet formation typically involves a protoplanetary disk swirling around a nascent star. The debris coalesces, gravity takes hold, and voila, a new planetary system is born. But that's only one side of the story. Imagine a cosmic mosh pit. Young star systems are chaotic places. Giant planets, in their early, unruly stages, can exert immense gravitational forces on their smaller siblings. According to research from institutions like NASA and various universities, these gravitational dance-offs, especially in crowded stellar nurseries, can be violent. A smaller planet might get too close to a gas giant, or experience a near miss with another forming world, and just like a slingshot, it can be hurled out of its home system at incredible speeds. Ejected, forever severed from the light of its parent star. And it's not just ejections. Sometimes a star itself can be ejected, or a small grouping of stars. In these scenarios, the planets still bound to those stars become rogue systems within the larger galactic context, but individual planets can still be orphaned. Another fascinating possibility, though less common for true planets, is that some of these objects might form directly from clouds of gas and dust that never quite had enough mass to ignite into a star. Think of them as stellar failures, but too big to be just a planet formed in a disk. We'll talk more about those later when we discuss brown dwarfs. But for now, let's focus on those ejected, truly planetary bodies. So, how do we find them? It's like trying to find a single grain of sand on a dark beach at night from orbit. But scientists have developed ingenious methods. One of the most successful is called gravitational microlensing. Here's how it works. Einstein's theory of general relativity tells us that massive objects bend space-time. This bending, in turn, deflects light. When a rogue planet passes directly in front of a much more distant background star, its gravity acts like a cosmic magnifying glass, temporarily brightening the light from that background star. It's a fleeting event, lasting anywhere from a few hours to a few days, and it requires precise observation. Imagine a tiny lens passing in front of a distant flashlight. You get a momentary flicker. According to a 2011 study published in Nature by an international team of astronomers using data from the MOA and OGLE surveys, they found a surprisingly high number of these events, suggesting that rogue planets are not just theoretical curiosities, but could be incredibly common. Later analyses, including one presented at the American Astronomical Society meeting in 2023, suggest there could be billions, perhaps even trillions, of these free-floating planets in our galaxy alone. They might outnumber stars. Let that sink in for a moment. More planets than stars, and most of them lost to the dark. So, what are these worlds like? Imagine a place where the sun never rises, where the only light comes from the faint, distant glow of other galaxies, or the occasional flash of a meteor. These worlds are plunged into eternal, deep cold. Surface temperatures would likely be just a few degrees above absolute zero, making them far colder than anything we experience on Earth, even in the depths of Antarctica. Any atmosphere they might have once possessed would be largely frozen solid or stripped away over eons, unless it was incredibly thick to begin with. But here's where the counterintuitive twist comes in, the true oddity. Could life exist on such a world? Our immediate instinct is a resounding no. No sunlight, no photosynthesis, no warmth. How could anything survive? But remember, our intuition is Earth-centric. And Earth has taught us a powerful lesson about extreme environments. Where there's energy, there's often life. The key to potential habitability on a rogue planet lies within the planet itself. Many rocky planets, especially larger ones, can retain a significant amount of internal heat. This heat comes from two main sources: radioactive decay of elements like uranium, thorium, and potassium in the planet's core and mantle, and residual heat from its formation, essentially the leftover warmth from when the planet was a molten ball. For a sufficiently large rogue planet, especially one with a significant amount of water ice, this internal heat could be enough to maintain a vast, subsurface ocean of liquid water, much like what we suspect exists under the icy shells of moons like Europa or Enceladus in our own solar system. Think about it. Beneath miles of frozen ice, isolated from the frigid surface, liquid water could persist for billions of years. And in that water, according to research on extremophiles here on Earth, life could thrive. It wouldn't be life dependent on photosynthesis, but rather chemosynthesis, drawing energy from hydrothermal vents on the ocean floor, much like the ecosystems found at the bottom of Earth's oceans, completely independent of the sun. These deep-sea ecosystems on Earth are fueled by chemical reactions, not sunlight, proving that life doesn't always need a star. Imagine these rogue ocean worlds, a seemingly dead, frozen sphere in the blackness, yet harboring a vibrant, chemically fueled biosphere hidden beneath its icy shell. It challenges our very definition of the habitable zone, that comfortable band around a star where liquid water can exist on a planet's surface. Rogue planets redefine it to an internal habitable zone. This phenomenon isn't just a quirky detail, it profoundly challenges our understanding of life's potential prevalence. If planets without stars can host life, then the cosmic landscape for biology expands dramatically. It means that the mere presence of a star is not a prerequisite for habitability. It means that even worlds considered dead by conventional definitions might be teeming with activity. The existence and potential abundance of rogue planets force us to broaden our cosmic vocabulary. What is a solar system if it doesn't have a sun? What is a planet if it has no star to orbit? These wanderers push the boundaries of our classifications and illuminate the sheer, beautiful diversity of celestial objects. They tell us that the universe is far more dynamic, far more chaotic, and far stranger than the neatly ordered diagrams in our textbooks suggest. So the next time you look at the stars, consider the vast, invisible populations of these lonely worlds, drifting silently through the cosmic night. They are a testament to the violent birth of planetary systems, the relentless power of gravity, and the surprising resilience of liquid water, and potentially life itself, even in the most extreme conditions imaginable. They are just the first of many cosmic oddities we're going to explore, each one peeling back another layer of our preconceived notions about the universe. Our intuition, again, is our enemy here. We picture planets as variations on a theme, rocky like Earth, gassy like Jupiter, maybe a bit hotter, a bit colder, a bit bigger, a bit smaller. But what if the very chemical ingredients that make up a planet are wildly different? What if the common elements we find in our solar system, silicon, oxygen, iron, magnesium, aren't universally dominant? Because, according to exoplanet surveys, they aren't. And when you change the recipe, you get some truly exotic and mind-bending worlds. Imagine a world where the mountains aren't granite or basalt, but glistening, colossal diamonds. Where the interior isn't a molten iron core, but a vast, solid diamond. This isn't fantasy, it's a very real possibility, and scientists have found compelling evidence for such diamond worlds. To understand how this happens, we need to think about stars. Our sun is relatively rich in oxygen. That oxygen readily combines with carbon to form compounds like carbon monoxide or carbon dioxide. But what if a star forms from a nebula that is unusually rich in carbon and poor in oxygen? If there isn't enough oxygen to lock up all the carbon, then the planets forming around such a star will have an abundance of free carbon. On a world with extreme pressure and heat, conditions found in the deep interiors of planets, carbon can crystallize into diamond. According to research from scientists at institutions like Arizona State University and Yale, if a rocky planet forms from material with a carbon to oxygen ratio greater than 0.8, it could be a diamond planet. Our solar system has a carbon to oxygen ratio of about 5, so Earth is rich in silicates and oxides. But a planet like 55 Cancri E, for instance, a super-Earth orbiting a star in the constellation Cancer, was once hypothesized to be a prime candidate for a diamond planet based on its mass, radius, and the chemical composition of its host star. While later observations nuanced that specific conclusion, the principle remains sound. The existence of stars with high carbon to oxygen ratios means diamond planets are not just theoretical curiosities, but a predictable outcome of stellar chemistry. Imagine what that means. An entire planetary crust, perhaps the entire mantle, made of compressed crystalline carbon. The ground underfoot would be diamond. The air, if any, would be thick with carbon monoxide or even more exotic carbon compounds. It's a glittering, alien landscape unlike anything our geology could ever produce. And it fundamentally changes how we think about planetary interiors, about geological activity, and even about the potential for life. What kind of tectonic plates would move on a diamond planet? What sort of mineralogy would define its core? These are open questions that push our understanding of planetary science to its absolute limits. Now, let's swing to the opposite end of the spectrum, still playing with chemical composition, but this time focusing on water. Earth is often called the water planet, and indeed, 2/3 of its surface is covered by liquid water. But we have a relatively thin layer. Our deepest oceans plunge about 11 kilometers. That's a lot for us, but cosmically, it's just a skin. What if there are worlds where water isn't just a surface feature, but the dominant constituent, making up a significant fraction of the planet's entire mass? We're talking about water worlds, or ocean planets, where the liquid layer could be tens, hundreds, or even thousands of kilometers deep. These aren't just giant Earths, they are fundamentally different. These worlds likely form further out from their stars, in regions where water ice is abundant. As the planet accretes, it gathers vast quantities of this ice. When it migrates inward or heats up due to internal processes, that ice melts, creating truly titanic oceans. Consider a world where the pressure at the bottom of such an ocean is so immense that water behaves in ways we can barely comprehend. We know water can turn into different forms of ice under pressure, even at high temperatures, exotic phases like Ice 7 or Ice X, which are structured differently from the ice cubes in your freezer. But on these extreme ocean planets, scientists theorize that beneath the liquid layer, there could be a layer of supercritical water where liquid and gas properties blur, followed by a layer of hot ice. Ice that's incredibly hot but still solid due to the crushing pressure. Below that, only then might you find a solid, rocky core. Imagine dropping into such an ocean. You'd descend through normal liquid water, then through a strange slushy transition, then through a layer of hot solid ice, before finally, perhaps, hitting rock. The chemistry of these oceans would be incredibly different. There would be no seafloor as we know it, no direct interaction between the ocean and a silicate mantle to drive plate tectonics and inject nutrients into the water. This lack of interaction is a critical point. On Earth, the continuous cycling of elements from the crust into the ocean, driven by volcanic activity and hydrothermal vents, is crucial for sustaining a diverse biosphere. On a deep-water world, life might struggle to find the necessary chemical building blocks if they are too diluted or locked away. However, the sheer volume of water on these worlds also presents intriguing possibilities. According to astronomers who analyze exoplanet data, planets like Kepler 22b, discovered by the Kepler Space Telescope, or GJ 2014b, are strong candidates for ocean worlds, potentially with deep, thick atmospheres composed largely of water vapor. Their existence stretches our definition of habitable once again. While the absence of a rock-water interface might be challenging, the possibility of life evolving in such vast, three-dimensional liquid environments remains a fascinating subject of astrobiological speculation. So, from diamond-crusted behemoths to worlds where water is the dominant geological feature from surface to core, these exotic exoplanet chemistries are a profound testament to the universe's boundless creativity. They show us that the formation of planets isn't a one-size-fits-all process. The elemental building blocks available in a stellar nursery, combined with the forces of gravity, pressure, and heat, can sculpt worlds that defy our wildest expectations. These discoveries are more than just fascinating curiosities. They force us to continuously refine our models of planet formation and evolution. They push the boundaries of what we consider possible for geology, chemistry, and even biology. And they remind us that the Earth, our blue marble, is not the template for all worlds, but a unique product of its specific cosmic circumstances. The universe, it turns out, prefers a much more eclectic palette. And these are just the beginning of the oddities we will encounter as we continue our journey. Next, we'll dive into worlds that never turn, locked in an eternal struggle between blazing day and freezing night. We've explored planets made of diamond and worlds drowned in endless oceans. But now, let's turn our attention not just to what planets are made of, but to how they move and how that movement, or lack thereof, can sculpt an alien landscape. On Earth, we have a day and night cycle. The sun rises, traverses the sky, and sets. Our planet spins, evenly distributing the sun's warmth and light across its surface over a 24-hour period. This rhythm of day and night is so fundamental to our lives, to our biology, to our sense of time, that we barely even think about it. It's a given, but out in the cosmos, for billions upon billions of planets, it's not. Imagine a world where the sun never moves in the sky. It hangs, perpetually fixed at one point. One side of the planet is locked in eternal daylight, blazing under the unwavering glare of its star. The other side is plunged into endless, freezing night, a realm of perpetual darkness. And between them, a narrow band of eternal twilight, a terminator zone, where the sun forever hovers near the horizon. These are tidally locked worlds, and they are not just theoretical curiosities. According to exoplanet surveys, particularly those focusing on planets orbiting M-dwarf stars, which are the most common stars in our galaxy, tidally locked planets are likely the norm, not the exception. Our own moon is tidally locked to Earth, always showing us the same face, and many of the exoplanets found within the habitable zones of smaller, cooler stars are expected to be tidally locked. It's a consequence of gravity, specifically tidal forces. If a planet is close enough to its star over billions of years, these tidal forces will slow its rotation until one side permanently faces the star. It's like a cosmic braking mechanism. Eventually, the planet's rotation period matches its orbital period. One rotation per orbit, permanent day, permanent night. Now, picture yourself on such a world. Step onto the day side, right under the star. The ground would be scorched, desiccated, potentially molten, depending on the star's heat. The air would be scalding, perhaps even blasted away into space by the intense stellar winds. On the night side, it would be a frozen wasteland, temperatures plummeting to hundreds of degrees below zero. Any atmospheric gases possibly condensed into vast glaciers of nitrogen, oxygen, or carbon dioxide ice. But the real drama, and the truly counterintuitive possibilities, lie in the atmosphere and its circulation. This extreme temperature gradient between the scorching day side and the freezing night side would create colossal, planet-spanning winds. Imagine a planetary-scale convection current. The superheated air from the day side would rise, flow towards the night side, cool, condense and sink, then flow back along the surface to the day side to be reheated. Models by atmospheric scientists, like those of the University of Exeter and NASA, suggest these winds could be ferocious, howling across the Terminator zone at supersonic speeds. It's a planetary-scale struggle between heat and cold, a permanent global storm system. Any clouds formed on the cooler night side might get blown over to the day side, only to evaporate instantly. But here's the interesting part. What about the Terminator zone? This narrow strip, often envisioned as a land of perpetual sunset or sunrise, could be the most intriguing place on such a world. Here, the temperatures might be moderate, not too hot, not too cold. The constant battle between day and night would likely create persistent, powerful weather systems. Clouds, if present, might be thick and permanent, trapping heat and potentially stabilizing temperatures further. Could life exist there? Again, our Earth-centric biases scream no. But consider this. If a tidally locked world has a thick enough atmosphere and sufficient water, the Terminator zone could be surprisingly temperate. The global atmospheric circulation would efficiently redistribute heat, preventing the day side from becoming completely unlivable and the night side from becoming a total deep freeze. Think of it like a giant heat pump, continuously moving energy around the planet. Scientists have found that some tidally locked planets orbiting M-dwarf stars are particularly promising candidates for habitability in their Terminator zones. The M-dwarf stars are smaller and cooler than our Sun, but they are also incredibly long-lived and abundant. Their habitable zones are much closer to the star, which is why tidal locking is so common there. The persistent twilight, the stable temperatures, the strong, unceasing winds, what kind of life would evolve in such an environment? Could there be plants that grow to track the static sun, or perhaps have evolved to draw energy from the extreme temperature gradients? Animals that migrate along the Terminator to stay within optimal conditions? Or perhaps entire ecosystems that harness the fierce winds? It's a canvas for evolutionary possibility. The concept of tidally locked worlds forces us to confront our ingrained assumptions about what makes a planet habitable. It tells us that a stable day-night cycle, while comforting and familiar to us, is not a universal requirement for life. It pushes us to imagine atmospheric dynamics and biological adaptations far beyond our terrestrial experience. These worlds, locked in an eternal embrace with their star, are not cosmic anomalies, but common occurrences. They are a testament to the powerful, shaping influence of gravity and the incredible diversity of conditions under which planets can exist. They are not merely exotic. They offer a new paradigm for understanding planetary climate and the distribution of life in the universe. And as we continue our journey, we'll see that even planets that seem to defy classification, like the enigmatic mini-Neptunes, hold equally fascinating oddities. Now, prepare for perhaps the most pervasive and perplexing cosmic oddity of all, the mini-Neptune. Take a look at our solar system's planets. We have the small, rocky terrestrial planets, Mercury, Venus, Earth, Mars. Then we jump straight to the gas giants, Jupiter and Saturn, colossal worlds primarily made of hydrogen and helium. And then the ice giants, Uranus and Neptune, still massive, but with a greater proportion of ices, like water, methane and ammonia, wrapped around solid cores. Notice something missing. There's a huge gap, a planetary size gap. We have nothing in our solar system that's significantly larger than Earth but smaller than Neptune. Nothing in between about 1.5 times Earth's radius, and 4 times Earth's radius. For decades, we assumed this was just how planets were. Then, exoplanet discoveries began pouring in thanks to missions like the Kepler Space Telescope. And what did we find? A cosmic explosion of planets that falls squarely into this missing size category. These are the mini-Neptunes, or sometimes called super-Earths with thick atmospheres. They are, quite simply, the most common type of planet known in the galaxy. Estimates suggest that up to 3/4 of all exoplanets detected are in this perplexing size range. Let that sink in. The most common planet type in the universe is one we don't have any example of in our own backyard. This is a fundamental challenge to our models of planet formation. Why are they so prevalent elsewhere, yet completely absent from our solar system? And what are they actually like? Imagine a world that's maybe 2 to 3 times the size of Earth, but significantly less dense. It would have a solid, rocky core, perhaps even an ocean or a layer of supercritical water, similar to what we discussed with ocean worlds. But crucially, wrapped around this core is a massive, extended atmosphere composed primarily of hydrogen and helium, possibly mixed with other volatiles like water vapor, methane, or ammonia. It's like a smaller, fluffier version of Neptune, but without the crushing gravity and immense size. The internal structure of these mini-Neptunes is a subject of intense debate and ongoing research. Are they essentially rocky super-Earths that managed to accrete a huge amount of primordial gas before their star blew it all away? Or are they scaled-down versions of gas giants, with much larger envelopes of hydrogen and helium relative to their core mass? It's like trying to tell if a bowling ball is just a heavy rock or a hollow sphere filled with air. The answer lies in their precise mass and radius measurements, which help determine their average density. And even with precise measurements, there are many possible internal compositions that can fit the data. One of the biggest mysteries about mini-Neptunes is their atmospheres. They are thought to be deep and opaque, making it incredibly difficult to observe their surfaces, if they even have a clearly defined surface. Unlike Earth's thin, breathable atmosphere, the atmospheric pressure on a mini-Neptune would be immense, crushing. Any water on the surface would be vaporized and potentially turn into exotic forms of hot, high-pressure ice or supercritical fluid deep within the atmosphere. This raises profound questions about habitability. Could a mini-Neptune host life? Our initial thought might be no. The crushing pressures, the hot, dense atmospheres, the lack of a defined surface. It doesn't sound very promising for life as we know it, but remember, the universe loves to surprise us. According to some theoretical models, if a mini-Neptune is located far enough from its star, or has just the right amount of internal heat, it might possess a liquid water layer above its rocky core, but below a massive hydrogen-helium atmosphere. Imagine an ocean shielded by an immense atmospheric blanket. This is a highly speculative scenario, and any life in such an ocean would be utterly alien, adapted to extreme pressures and darkness. Another major puzzle surrounding mini-Neptunes is the Fulton Gap, or radius gap. When astronomers plot the sizes of exoplanets, they notice a curious dip in the distribution around 1.5 to 2 times Earth's radius. It's as if planets either grow to be super-Earths, rocky, with thin atmospheres, or jump over this gap to become mini-Neptunes with thick hydrogen-helium envelopes. There aren't many planets right in the middle of this gap. What causes this gap? Scientists have proposed several explanations. One leading theory involves photoevaporation, where the intense radiation from a star slowly strips away the outermost layers of a planet's atmosphere. If a young planet forms with a small hydrogen-helium envelope, stellar radiation might eventually erode it completely, leaving behind a bare, rocky super-Earth. However, if the planet manages to accrete a really substantial envelope, it becomes too massive for the stellar radiation to strip it away entirely, resulting in a mini-Neptune. The gap, therefore, might represent the tipping point, where a planet either loses its puffy atmosphere or retains it. Another theory involves the amount of gas available during planet formation. Perhaps there simply isn't enough gas in many protoplanetary disks to form planets that would fall into that intermediate size range. Or perhaps there are unique mechanisms of core accretion where cores either don't grow large enough to capture massive atmospheres, or they grow so fast that they capture a lot, leaving little in between. The mini-Neptunes, these enigmatic, ubiquitous worlds, are a stark reminder that our solar system is not a universal template. Its particular arrangement of planets, the specific chemical abundances of its star, and the timing of its formation all contributed to the unique family of planets we call home. The rest of the galaxy, it turns out, plays by slightly different rules, leading to a planetary zoo far more diverse and surprising than we ever imagined. Understanding mini-Neptunes is a frontier in exoplanet research. Missions like the James Webb Space Telescope are now peering into their atmospheres, trying to decipher their compositions and temperatures. What they uncover will not only shed light on these mysterious worlds, but will also provide crucial clues about the fundamental processes of planet formation and evolution across the cosmos. These common, yet utterly alien worlds are a perfect example of how the universe continues to confound our expectations, offering mysteries even in the most abundant of its creations. And speaking of things that defy easy classification, our next oddity exists in a grey area between planets and stars, the enigmatic brown dwarfs. Let's consider objects that blur the very definition of what a planet is and what a star is. Objects that occupy a fascinating, ambiguous space in the cosmic classification system. These are the brown dwarfs, the failed stars. When you look up at the night sky, you see stars. Glorious, burning orbs of plasma, radiating light and heat for billions of years, fueled by the relentless process of nuclear fusion in their cores. That's the hallmark of a star, the ability to fuse hydrogen into helium, releasing immense energy. On the other end of the spectrum, you have planets, objects like Jupiter, massive, yes, but not hot enough, not dense enough to sustain fusion. Brown dwarfs exist right in that uncomfortable middle ground. They're too big to be considered planets, typically ranging from about 13 times the mass of Jupiter up to about 80 times Jupiter's mass. If they were any lighter, they'd be gas giants. If they were any heavier, they'd ignite nuclear fusion and become true stars, albeit very dim red dwarfs. They just can't quite make it. They are stellar wannabes that never reach their full potential. Imagine a cosmic oven. A star is an oven that gets hot enough to cook all its ingredients, to fuse hydrogen. A planet is like a mixture that never gets turned on. A brown dwarf, however, is an oven that gets turned on, heats up, but just barely. It gets hot enough to briefly fuse deuterium, a heavier isotope of hydrogen, and sometimes even lithium, but it can't sustain the fusion of regular hydrogen. That fusion is what powers long-lived stars like our Sun. So, for a brief flicker in their youth, brown dwarfs shine a bit brighter from this temporary fusion. But then, they just fade. They slowly cool down, contracting under their own gravity, radiating away their residual heat. They never truly ignite in the stellar sense. This cooling process makes them incredibly dim and difficult to detect. They don't emit much visible light. Instead, they primarily glow in the infrared, like a slowly cooling ember. This is why it took until the mid-1990s to definitively confirm their existence. According to a seminal paper in Nature in 1995, the object Gliese 229b was identified as one of the first unambiguous brown dwarfs, a companion to a red dwarf star. Since then, infrared sky surveys like WISE Wide Field Infrared Survey Explorer have revealed thousands of them, showing they are quite common. Some estimates suggest there could be as many brown dwarfs as stars in our galaxy, perhaps even more. So, what are they like? A brown dwarf is a truly alien world. Its gravity is immense, far stronger than any planet in our solar system. Its interior is under incredible pressure, yet it doesn't reach the fusion temperatures of a star. The atmosphere is a bizarre brew, unlike anything we see on planets or stars. Think about Jupiter. It has clouds of ammonia and water. Now imagine something similar, but far, far hotter and more massive. Brown dwarfs have complex, dynamic atmospheres with roaring winds and giant storms. But because they are cooling, their atmospheric chemistry changes over time. Hotter brown dwarfs might have clouds of molten iron and silicate dust, raining down liquid metal or glassy pebbles. As they cool, these exotic clouds condense and fall, replaced by clouds of methane, water, or ammonia, much like Jupiter, but still at far higher temperatures. Scientists, using instruments like the James Webb Space Telescope, are now beginning to probe these atmospheres with unprecedented detail. They're looking for specific chemical signatures that tell us about the temperature, pressure, and composition of these fascinating objects. According to recent JWST observations of objects like LHS 475b and other brown dwarf systems, we're seeing complex atmospheric layering, hints of unexpected cloud structures, and a chemistry that is constantly evolving as the dwarfs cool over billions of years. The defining characteristic of brown dwarfs, aside from their mass, is their degeneracy. In their cores, the matter is so compressed that the electrons are squeezed together as tightly as quantum mechanics allows. This electron degeneracy pressure is what prevents them from collapsing further and igniting into a star. It's the same force that supports white dwarf stars, which are much denser, stellar remnants, but for brown dwarfs it happens at a lower mass threshold. It's like a cosmic spring holding the object up against the relentless pull of gravity. Brown dwarfs play a unique role in the cosmic ecosystem. They aren't stars, so they don't contribute directly to the light and heat budget of the galaxy in the way stars do. But they are a significant mass component. Many have been found as solitary wanderers, much like the rogue planets we discussed earlier. They are a testament to the fact that star formation doesn't always go according to plan. Sometimes, the gas cloud just isn't quite massive enough. They also offer fascinating insights into planetary formation. Some brown dwarfs have planets orbiting them. So, you can have a failed star acting as a sun to a system of planets. This further blurs the lines. What exactly defines a solar system when the central object isn't a star, but something in between? Brown dwarfs challenge our neat categories, forcing us to think about a continuum rather than hard boundaries. They remind us that the universe is a messy, beautiful laboratory, constantly experimenting with different combinations of mass, gravity, and chemistry. They are the cosmic in-betweens, objects that embody the idea that the universe is full of entities that don't quite fit our preconceived boxes. They are too big to be planets, yet too small to be stars. They are the ultimate cosmic tweenagers, stuck in an awkward but utterly captivating phase of cosmic evolution. And speaking of extreme conditions, if brown dwarfs represent a failure to ignite, our next oddity is the terrifyingly dense remnant of stars that exploded spectacularly, the neutron stars. Let's take a terrifying leap into the aftermath of stellar death, where the universe showcases its most extreme physics. We're going to talk about neutron stars, objects so dense, so extreme, that they defy ordinary comprehension. Imagine a star much more massive than our Sun, perhaps 8 to 20 times its mass. These giants live fast and die young. When they exhaust their nuclear fuel, their cores collapse catastrophically. The outer layers rebound in a spectacular supernova explosion, briefly outshining entire galaxies. If the core is massive enough, yet not too massive, it doesn't become a black hole. Instead, it collapses into something utterly extraordinary, a neutron star. Think about an atom. It's mostly empty space, right? A tiny nucleus surrounded by electrons whizzing around. Now imagine squeezing all that empty space out. Imagine collapsing an entire mountain into the size of a sugar cube. That's essentially what happens in a neutron star. The gravitational collapse is so intense that electrons are forced into atomic nuclei, combining with protons to form neutrons. The entire star becomes one giant atomic nucleus, held together by the strong nuclear force. The numbers are mind-boggling. A typical neutron star has a mass of about 1.4 to 2 times that of our Sun, but it's crammed into a sphere only about 20 kilometers or 12 miles across. That's the size of a city. Take all the mass of our Sun, condense it into something the size of Manhattan. This means their density is unimaginable. A single teaspoon of neutron star material would weigh billions of tons. To put it another way, if you could take all the cars in the world, stack them on top of each other, and compress them down to the size of a marble, that marble would still be far, far less dense than a speck of neutron star material. The gravity at its surface is billions of times stronger than Earth's. If you dropped a marshmallow onto a neutron star, it would hit the surface with the force of a 1,000-ton asteroid. And it gets stranger. These objects are spinning incredibly fast. When a massive star collapses, it conserves its angular momentum. Think of an ice skater pulling in their arms to spin faster. A star, collapsing from hundreds of thousands of kilometers down to just 20, will spin up dramatically. Many neutron stars are observed as pulsars, cosmic lighthouses that beam radiation from their magnetic poles. As they spin, these beams sweep across Earth, creating precise, rhythmic pulses like a cosmic clock. Some pulsars spin hundreds of times per second, faster than a kitchen blender. This incredibly precise timing has even allowed scientists to use them as natural cosmic clocks to test theories of general relativity. According to research by Hulse and Taylor in the 1970s, their observations of a binary pulsar provided the first indirect evidence for gravitational waves, a prediction of Einstein's theory. The interior of a neutron star is a realm of exotic physics. It's theorized to have layers, an outer crust of heavy nuclei and electrons, then an inner crust where neutrons start to drip out of the nuclei, followed by a liquid core of pure, neutron-rich matter. Below that, the conditions are so extreme that even neutrons might break down into their constituent quarks, a theoretical state of matter called quark-gluon plasma. We'll delve into that mind-bending idea in the next subtopic. But neutron stars aren't just dense and fast. Some of them possess the most powerful magnetic fields in the universe. These are the magnetars. Their magnetic fields are a quadrillion times stronger than Earth's. To visualize this, consider our sun's magnetic field, which is powerful enough to create sunspots and solar flares. A magnetar's field is about 1,000 trillion times stronger than that. What happens in such an extreme magnetic field? It literally warps space-time around the magnetar. It can tear apart atoms, stripping away their electrons, leaving behind bare nuclei. It can cause starquakes in the neutron star's crust, releasing enormous bursts of X-rays and gamma rays that are so powerful they can affect Earth's atmosphere even from across the galaxy. These are known as soft gamma repeaters and anomalous X-ray pulsars, and they represent the most extreme magnetic phenomena known. According to research from groups studying these cosmic giants, the energy released in a magnetar flare can, for a fleeting moment, exceed the energy output of our sun over 100,000 years. The sheer power is almost incomprehensible. It's like the universe's ultimate cosmic amplifier, taking a relatively small amount of energy and magnifying it through an unparalleled magnetic field. Neutron stars, particularly pulsars, have also been instrumental in our understanding of fundamental physics. Their stability and precision have allowed for tests of gravity in extreme conditions, and they are crucial tools for detecting gravitational waves, a topic we'll explore in detail later. They are laboratories for quantum chromodynamics, general relativity, and plasma physics, all rolled into one impossibly dense package. So, from the comforting blue marble we began with, we've now plunged into the heart of a dead star, a city-sized remnant that packs the mass of 2 suns into a sphere of pure nuclear matter, spinning hundreds of times a second, and often wrapped in a magnetic field so powerful it can shatter atoms. Neutron stars are not just oddities, they are a testament to the universe's capacity for extremes, pushing the boundaries of what matter and energy can become. They are a terrifying and wondrous reminder that the cosmos holds phenomena far beyond our wildest imaginings, and some of these oddities are only just beginning to reveal their secrets. What could be even stranger? Perhaps matter even more crushed, beyond neutrons. Welcome to the theoretical frontier of quark stars. To understand quark stars, we need to zoom in even further than the neutron. Remember, protons and neutrons themselves aren't fundamental particles. They are made up of even smaller constituents called quarks. Specifically, protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks. These quarks are held together by the strong nuclear force, mediated by particles called gluons. This is the realm of quantum chromodynamics, where the rules of physics get truly strange. Inside a neutron star, the neutrons are packed incredibly tightly. They are supported against further collapse by what's called neutron degeneracy pressure. It's the quantum mechanical principle that prevents identical particles, like neutrons, from occupying the same quantum state. It's an incredibly powerful force, but even it has its limits. The theory suggests that if a neutron star is particularly massive, perhaps exceeding a certain upper mass limit that is still debated, somewhere around 2 to 3 solar masses, the pressure in its core could become so extreme that even the neutrons themselves are crushed. The strong nuclear force that binds the quarks within individual protons and neutrons might be overcome. The quarks would be set free from their confinement, forming a continuous soup of up, down, and even strange quarks. This hypothetical state of matter is known as quark matter, or sometimes strange quark matter if strange quarks are involved, and a star made predominantly of this stuff would be a quark star. Imagine, if you can, a star that is even denser than a neutron star. A quark star would be even smaller, perhaps only 10 to 12 kilometers across, yet still containing up to 2 or 3 times the mass of our Sun. The density would be beyond astronomical. It would be quantum mechanical. A teaspoon of quark matter would weigh quadrillions of tons, far more than that neutron star material we just discussed. It's like taking the entire Earth and compressing it down to the size of a football stadium. This isn't just a slight adjustment to neutron star physics, it's a phase transition, like water turning into ice, but at a fundamental particle level. The very building blocks of matter would have changed their state. Protons and neutrons, the stable components of atomic nuclei, would no longer exist as distinct entities. The idea of quark stars has been around since the 1970s, but they remain purely theoretical. Why? Because the conditions required are so extreme, and the physics of quark matter is incredibly complex and not fully understood. Scientists are still trying to pin down the exact equation of state for matter at such densities. So, how would we find one? How would we distinguish a quark star from an extremely dense neutron star? This is the core challenge. They would look very similar, incredibly small, incredibly dense, rapidly spinning objects. But there are subtle differences scientists are looking for. One potential signature could be their mass-radius relationship. According to theoretical models, a quark star might have a slightly different mass-radius curve compared to a neutron star. If we could precisely measure the radius of a very massive neutron star, and it turns out to be smaller than predicted by neutron star models, that could be a clue. However, measuring the radius of something 12 kilometers across, billions of light years away, is an incredible technical challenge, even with advanced observatories. Another potential clue could be their cooling rate or their vibrational modes after a cosmic collision. If 2 neutron stars merge, they create gravitational waves. The ring-down phase after the merger, the way the remnant object vibrates and settles, could carry signatures that differentiate between a super-dense neutron star and a newly formed quark star. The LIGO and Virgo gravitational wave detectors are now providing data that might, one day, allow us to see such a subtle difference. Some scientists have also suggested that quark stars might have unique surface properties. The crust of a quark star, if it exists, might behave differently from a neutron star's crust. It might even have a small layer of exotic heavy nuclei, if such a thing could form. The search for quark stars represents the cutting edge of astrophysics and nuclear physics. It's about understanding the fundamental behavior of matter under the most extreme conditions the universe can produce. It's about pushing the boundaries of our knowledge of the strong nuclear force itself. Are protons and neutrons truly the final, unbreakable building blocks of the stars? Or are they just temporary arrangements, destined to be crushed into their constituent quarks under enough pressure? The possibility of quark stars forces us to reevaluate what we mean by matter at its most fundamental level. If they exist, they represent an even more exotic state than anything we can recreate in even the most powerful particle accelerators on Earth. They would be a testament to the universe's relentless ability to compress and transform, revealing layers of physics we are only just beginning to grasp. So, when we look at a neutron star, we might not just be looking at a sphere of neutrons. We might be looking at a gateway to hyperspace for matter, a state where particles we once considered fundamental have broken down, revealing an even deeper layer of cosmic strangeness. They are a profound question mark in the heart of the most collapsed objects, urging us to continue our search for the ultimate truth of the cosmos. And speaking of extreme motions and strange origins, next we'll explore objects that are flung out of galaxies at immense speeds, the hypervelocity stars. Let's shift our perspective dramatically. from the extreme density of matter to the extreme motion of matter. Imagine a star, not peacefully orbiting within its galaxy, but hurtling through space at speeds so immense it's destined to escape its galactic home forever, cast out into the cold, dark void between galaxies. These are hypervelocity stars. Think of our Sun. It orbits the center of the Milky Way at a speed of about 220 kilometers per second, or about 490,000 miles per hour. It's a stately, predictable journey, taking about 230 million years to complete one full revolution. It's bound by the gravity of the Milky Way, part of the galactic dance. But a hypervelocity star, these objects travel at speeds exceeding the escape velocity of their galaxy. For the Milky Way, that's about 500 kilometers per second, or over 1 million miles per hour. That means they're moving so fast that our galaxy's immense gravity simply can't hold on to them anymore. They are on a one-way trip, destined to become cosmic exiles, forever roaming intergalactic space. It sounds like a tragic fate for a star, doesn't it? Like being shot out of a cosmic cannon. But how does this even happen? What kind of forces could accelerate an entire star to such incredible speeds? The primary suspect, the undisputed cosmic slingshot champion, is the supermassive black hole at the center of nearly every galaxy. Our own Milky Way harbors Sagittarius, RSSSS, a black hole with the mass of 4 million suns. This gravitational monster is the key to understanding hypervelocity stars. Imagine a binary star system, two stars orbiting each other, venturing too close to Sector A. As the pair approaches the black hole's intense gravitational field, it experiences extreme tidal forces. The black hole's gravity can grab one of the stars, capturing it into a tight orbit, or even consuming it. It can be flung out at incredible speeds, kicked away like a pebble from a giant's foot. This is the leading mechanism for creating hypervelocity stars, according to numerical simulations and theoretical models developed by astronomers. Think of it like a three-body problem in extreme conditions. The black hole, the two stars, one gets pulled in, the other gets launched out. It's a chaotic but efficient way to accelerate a star to escape velocity. The first hypervelocity star, named HEO 4375439, was discovered in 2005. Its speed and trajectory clearly showed it was on its way out of the Milky Way. Since then, dozens more have been found. We can trace their paths backward in time, confirming that many originate from the galactic center. These stars aren't just fascinating because of their incredible speed, they are also incredibly valuable tools for astronomers. Their trajectories can tell us about the distribution of mass, including elusive dark matter, in the galactic halo. Because they're traveling so fast and are relatively unimpeded, they act like cosmic probes, giving us clues about the gravitational potential of the entire galaxy. According to research by scientists at the Harvard-Smithsonian Center for Astrophysics and other institutions, analyzing the paths of these stars can help map the mysterious distribution of dark matter that holds our galaxy together. What else can create these cosmic cannonballs? While the supermassive black hole ejection mechanism is dominant, other scenarios are also possible, though less common. For instance, the explosion of a particularly asymmetric supernova in a binary system could give its companion star a powerful kick. Or, in extremely dense star clusters, close encounters between multiple stars could, rarely, result in one being ejected at high speed. However, the sheer energy required to accelerate an entire star to escape velocity typically points to the immense gravitational power of a supermassive black hole. What's the fate of a hypervelocity star? It will spend billions of years, perhaps tens of billions, traversing the vast, dark emptiness between galaxies. It will eventually burn through its nuclear fuel, just like any other star, albeit in profound isolation. It might end its life as a white dwarf, a neutron star, or even a black hole, but it will do so far from its birthplace, a lone beacon fading in the intergalactic night. It's a poignant thought, a star born in the vibrant heart of a galaxy, destined to die in the cosmic wilderness. The existence of hypervelocity stars paints a more dynamic, and at times violent, picture of galactic centers than we might intuitively imagine. Far from being serene hubs of stellar life, the regions around supermassive black holes are extreme gravitational arenas where stars are ripped apart, captured, or flung away with incredible force. These stars force us to consider the universe not just as a collection of static objects, but as a place of immense power and constant transformation. They are a vivid illustration of how gravity, when concentrated in objects like supermassive black holes, can be a force of both creation and destruction, binding galaxies together while simultaneously tearing apart their stellar inhabitants and casting them out into the void. They are a powerful reminder that our intuitive notion of a peaceful, orderly cosmos is constantly being challenged by the incredible discoveries made by astronomers. And speaking of cosmic violence, if hypervelocity stars are the bullets, our next oddity is the ultimate cosmic explosion, gamma-ray bursts, the universe's most powerful blasts. We've seen stars flung out of galaxies by supermassive black holes, a testament to the powerful, sometimes violent, dynamics of the cosmos, the kind that makes a supernova look like a firecracker. We're going to talk about gamma-ray bursts, or GRBs, the most powerful explosions in the universe. Imagine an event that, for a few fleeting seconds or minutes, can outshine an entire galaxy of hundreds of billions of stars. An event that releases more energy than our sun will produce over its entire 10 billion year lifespan, all concentrated into a narrow beam of incredibly high energy radiation. This is what a gamma-ray burst is. These mysterious flashes of gamma rays were first detected accidentally in the late 1960s by American military satellites designed to look for secret nuclear weapons tests. They were a puzzle for decades. Were they coming from within our galaxy, from nearby stars, or from the very edges of the observable universe? It took until the late 1990s and early 2000s, with dedicated satellites like Bepo's-AX and Swift, to finally pinpoint their origins and truly understand their immense power. There are generally two main types of GRBs, classified by their duration: short GRBs, lasting less than about 2 seconds, and long GRBs, lasting from a few seconds to several minutes. While they both unleash incredible energy, their origins are fundamentally different, and both involve some of the most extreme cosmic oddities we've already touched upon. Let's start with long GRBs. These are now understood to be the birth cries of black holes forming from the collapse of massive, rapidly rotating stars. Think back to those massive stars we discussed when talking about neutron stars, stars many times heavier than our sun. When such a star dies, its core collapses. If the core is massive enough, it doesn't stop at a neutron star, it collapses all the way down to a black hole. But it's not just any massive star. It needs to be a very specific kind, a rapidly spinning, very massive star that has shed most of its outer hydrogen envelope. This leaves a dense exposed core. When this naked core collapses, the material around the newly formed black hole creates an accretion disk. Powerful jets of plasma are launched from the poles of this system, punching through the collapsing star and erupting outwards at nearly the speed of light. It's like a cosmic drill boring its way through the star. It's the moment these jets break free that we observe the burst of gamma rays. Imagine a star collapsing in on itself, but instead of just imploding, it channels a colossal amount of energy into two narrow relativistic beams. If one of those beams happens to be pointed straight at Earth, we see a long GRB. According to extensive observations, including those from the Hubble Space Telescope and ground-based observatories, long GRBs are typically associated with a type of supernova called a hypernova or collapsar, confirming their origin from massive star collapse. Now, short GRBs. These are even more exotic and involve a phenomenon we'll discuss in more detail later: the merger of compact objects, specifically two neutron stars or a neutron star and a black hole. Imagine two neutron stars, those incredibly dense city-sized remnants we just talked about, spiraling inward toward each other. They're locked in a deadly dance, slowly losing energy through gravitational waves. As they get closer, they distort each other, eventually colliding and merging in an unimaginably violent event. This collision creates a tremendous burst of gravitational waves, which we've now directly detected, and also throws off a massive amount of neutron-rich material. This material rapidly decays and heats up, producing a short, intense burst of gamma rays, often accompanied by a unique electromagnetic signature called a kilonova. The detection of the gravitational wave event, GW708117 in 2017, followed just seconds later by a short GRB and a kilonova, provided definitive proof of this mechanism. According to research published in Physical Review Letters by the LIGO and Virgo collaborations, this multi-messenger astronomy event confirmed the origin of short GRBs and cemented our understanding of neutron star mergers. So, these are the universe's most powerful explosions, occurring billions of light years away. They are so luminous that they allow us to probe the very early universe, acting as cosmic flashlights that illuminate distant galaxies that would otherwise be too faint to see. They are tools for cosmology, helping us understand star formation rates and the chemical evolution of the universe at its infancy. But GRBs also have a darker side. They pose a potential existential threat. If a GRB were to occur in our own galaxy, with its beam pointed directly at Earth, the consequences would be catastrophic. The burst of gamma rays would strip away a significant portion of our planet's ozone layer, exposing life to lethal levels of ultraviolet radiation from the sun. It could trigger a mass extinction event. While the likelihood of such an event happening close enough and pointed at us is incredibly low, it's a sobering reminder of the violent power lurking in the cosmos. Gamma ray bursts are truly cosmic oddities, fleeting, incredibly powerful, and profoundly significant. They are the ultimate testament to the universe's capacity for both creation and destruction, providing insights into the most extreme stellar deaths and mergers, and pushing the boundaries of what we thought was possible in terms of energy release. They are cosmic fireworks, simultaneously beautiful and terrifying, reminding us that we live in a dynamic, sometimes violent, but always awe-inspiring universe. And speaking of things that defy their supposed fate, next we'll meet stars that cheat cosmic death, the blue stragglers. Now, let's turn our attention to stars that, instead of dying dramatically, seem to cheat death altogether. These are the blue stragglers, cosmic rebels that defy the natural order of stellar evolution. When you look at a star cluster, a group of stars born at roughly the same time from the same cloud of gas and dust, you expect them all to be at similar stages of their lives. Massive, hot, blue stars burn through their fuel quickly and die young. Smaller, cooler, red stars live for much longer. This is the stellar evolutionary clock, a fairly predictable process. If you observe an old cluster, you expect to see mostly older, redder stars, with the massive blue ones long gone. But in 1953, astronomer Alan Sandage made a puzzling discovery in the globular cluster, M3. Amidst a population of predominantly old, red, yellowish stars, he found some bright blue stars. They were hotter, more massive, and appeared much younger than their neighbors. They shouldn't have been there. They were straggling behind the evolutionary timeline of the cluster. Thus the name blue stragglers. It's like looking at a classroom of elementary school children and then noticing a few fully grown adults sitting among them. They stand out. They defy expectation. So, how do these stars cheat their stellar fate? How do they manage to appear younger and more massive than their coeval peers? For decades, blue stragglers were a profound mystery. But thanks to detailed observations, particularly from the Hubble Space Telescope and advanced stellar modeling, we now have a much clearer picture. The answer lies in stellar cannibalism, or, more politely, stellar mergers. Imagine two stars in a tight binary system, orbiting each other closely. As the more massive of the two stars evolves, it expands into a red giant. If it expands enough, it can actually transfer some of its mass to its smaller companion. The smaller star, now acquiring fresh hydrogen fuel, gets a new lease on life. It becomes more massive, hotter and bluer, appearing to rejuvenate. It's like a cosmic transfusion, giving the recipient star a second youth. According to research on stellar dynamics in dense clusters, this mass transfer in binary systems is a key mechanism for creating blue stragglers. But there's an even more dramatic scenario: direct stellar collisions or mergers. Star clusters, especially dense globular clusters, are crowded places. Stars are relatively close to each other. If two stars in a cluster have a close encounter, or if a binary system encounters another star, the gravitational interactions can become incredibly chaotic. Sometimes, these interactions can lead to two stars actually colliding and merging. Think of it like two drops of water merging into a larger drop. When two stars merge, their total mass combines. This new, more massive star suddenly has a much larger supply of hydrogen fuel in its core. It essentially gets a reset on its evolutionary clock. It heats up, burns brighter, and takes on the appearance of a much younger, more massive blue star, even though it formed from two older, smaller stars. Studies by astronomers at institutions like the University of Cambridge, using sophisticated simulations, have shown that direct collisions can indeed form blue stragglers, particularly in the dense cores of globular clusters where encounters are more frequent. The evidence for these merger events is often subtle. Sometimes, blue stragglers show unusually rapid rotation, a remnant of the angular momentum from the merging stars. In other cases, their atmospheric composition might show anomalies that hint at a violent past. But the sheer number of blue stragglers found, particularly in dense stellar environments, strongly supports these interaction and merger hypotheses. Blue stragglers are more than just cosmic curiosities. They are invaluable natural laboratories for studying stellar evolution, binary star interactions, and the dynamics of star clusters. They show us that stellar evolution isn't always a straightforward, linear process. It can be profoundly affected by the environment in which a star lives. In crowded stellar neighborhoods, stars don't always evolve in isolation. They can interact, merge, and dramatically alter their destinies. They also challenge our assumptions about how we date stellar populations. If you simply look at the color and brightness of a blue straggler, you might incorrectly assume it's a young star, throwing off your age estimates for an entire cluster. Understanding these stellar imposters is crucial for accurately mapping the cosmic timeline. The existence of blue stragglers reminds us that even within the seemingly predictable realm of stellar evolution, there are exceptions, twists, and turns. Stars, like everything else in the universe, are subject to the chaotic, often violent, forces of gravity and interaction. Some manage to find a way to defy their apparent fate, burning brighter and longer by consuming their companions or merging with others. They are a testament to the universe's ingenuity in creating unexpected phenomena, showing that even in the dying embers of a star cluster, new, brighter lights can emerge. And speaking of incredible gravitational forces that govern the fate of stars, next, we finally delve into the most famous cosmic oddity of all, black holes. Now we come to perhaps the most iconic and frequently misunderstood cosmic oddity, the black hole. For many, the term black hole conjures images of a cosmic vacuum cleaner, a giant mouth sucking up everything in its path, an insatiable monster lurking in the dark. It's a popular image, but it's also profoundly misleading. Black holes are far stranger, far more complex, and in some ways, far more elegant than this simplified caricature. So, let's cut through the myths. What is a black hole, really? It's not an object in space. It's a region of space-time where gravity is so incredibly strong that nothing at all, not even light, can escape. It's the ultimate gravitational prison. How does such a region form? Imagine a massive star, much larger than our sun, reaching the end of its life. Like the stars that form neutron stars, its nuclear fuel runs out. The outward pressure from fusion ceases and gravity wins. The core collapses in on itself. But this time, it's too massive to stop at a neutron star. The collapse continues, relentlessly, until all its mass is compressed into an infinitesimally small point called a singularity. This singularity is not the black hole itself. It's the incredibly dense point at the heart of the black hole. The black hole is the region around that singularity where the escape velocity exceeds the speed of light. This boundary, the point of no return, is called the event horizon. Think of it like this. Imagine a river flowing towards a waterfall. Upstream, you can swim against the current and escape. But as you get closer to the edge, the current becomes too strong. No matter how hard you swim, you're inevitably carried over the falls. The event horizon is that invisible line in the cosmic river. Once you cross it, you're trapped. Even light, traveling at the universe's speed limit, can't fight its way out. This is why they are black. Not because they are literal holes in space, but because no light can escape them. They are perfectly dark, and they are not cosmic vacuum cleaners. If our sun were suddenly replaced by a black hole of the same mass, Earth would continue to orbit it exactly as it does now. It wouldn't get sucked in. Why? Because the black hole's gravity would be the same as the sun's at our distance. Black holes only become sucky when you get very, very close to them, near the event horizon. So, if they're invisible, how do we detect them? We can't see them directly, but we can see their profound influence on their surroundings. Imagine a dancer in a completely dark room. You can't see the dancer, but you can see the way the other dancers move around them, pulled into their orbit or flung away. One way we detect stellar mass black holes, those formed from collapsed stars, is by observing their effects on companion stars. If a black hole is part of a binary system, it can pull gas from its companion star. This gas doesn't just fall straight in, it spirals around the black hole, forming an incredibly hot accretion disk. As the gas rubs together, it heats up to millions of degrees, emitting powerful X-rays that we can detect with X-ray telescopes. According to research from observatories like NASA's Chandra X-ray Observatory and ESA's XMM Newton, these X-ray emissions are one of the clearest signs of an active black hole. Another way is through gravitational waves. As we briefly touched on with short gamma-ray bursts, the merger of two black holes creates immense ripples in the fabric of space-time, gravitational waves, which we can now detect directly. The groundbreaking discovery of gravitational waves by LIGO in 2015 came from two colliding black holes. This opened an entirely new window onto the universe and confirmed the existence of black holes in a spectacular way. And what about the idea of a black hole having hair? This refers to a concept from general relativity called the no-hair theorem. It states that once a black hole forms and settles down, it quickly loses almost all information about the star it came from. The only properties an outside observer can measure are its mass, its angular momentum, spin, and its electric charge, though most astrophysical black holes are expected to be electrically neutral. Pop. All other hair, all other distinguishing features of the star, are lost behind the event horizon. So, in essence, all black holes of the same mass, spin, and charge are identical. It's an incredibly profound and counterintuitive idea. The existence of black holes, first predicted by Einstein's theory of general relativity, is a triumph of theoretical physics and observational astronomy. They are not merely exotic objects. They are fundamental components of the universe, shaping galaxies, influencing star formation, and pushing the boundaries of our understanding of gravity and space-time. They are the ultimate gravitational oddity, a place where our everyday intuition about solid objects and empty space completely breaks down. They are a profound challenge to our understanding of information, causality, and the very nature of reality itself, and the journey into their mysteries has only just begun. From their strange properties to their terrifying effects, black holes represent the pinnacle of cosmic strangeness. And speaking of terrifying effects, next we'll take a visceral, hypothetical dive into what would happen if you actually fell into one. What truly happens at that infamous boundary, the event horizon? Let's embark on a hypothetical, deeply uncomfortable journey into the heart of a black hole. Not a supermassive one just yet, but a stellar mass black hole, perhaps one born from a star about 10 times the mass of our Sun. These are the black holes where the weirdness truly begins to manifest in a visceral, physical way. Imagine you're an intrepid, or perhaps foolish, explorer piloting a spaceship towards a stellar mass black hole. As you approach, you notice something subtle at first. Objects around you, even distant ones, seem to distort. Their light is bent, stretched, and magnified by the black hole's intense gravity, acting like a cosmic funhouse mirror. This is gravitational lensing on an extreme scale. But the real drama begins when you get closer. On Earth, gravity pulls uniformly on your entire body. The difference in gravitational pull between your head and your feet is negligible. Not so near a black hole. The gravitational force diminishes rapidly with distance. This means that if you're falling feet first towards a black hole, the gravitational pull on your feet will be significantly stronger than the pull on your head. The black hole is so compact that it's also pulling more strongly on the parts of your body closer to its center, pulling them inwards, while also squeezing you from the sides. This differential gravitational force is called tidal force. And near a stellar mass black hole, these tidal forces become overwhelming. As you fall, your body would begin to stretch lengthwise, while simultaneously being squeezed horizontally. Imagine taffy being pulled and narrowed. That's you. you would be stretched into a long, thin, spaghetti-like strand of matter. This gruesome yet scientifically accurate process is known as spaghettification. It's a terrifying thought. Every atom in your body, every molecule, would be subjected to immense tearing forces. Your bones would snap, your muscles would shred, and eventually, even the bonds between your atoms would break. You wouldn't just be dead, you'd be disassembled into a stream of fundamental particles, stretched out over thousands of kilometers. This gruesome fate would occur even before you reach the event horizon of a stellar mass black hole. Now, let's talk about the event horizon itself. This isn't a physical surface. You wouldn't feel a thump or see a line in space. The event horizon is a mathematical boundary defined by the point where the escape velocity exactly equals the speed of light. If you cross it, you won't immediately know you've done so. You'll just continue to fall. But everything changes for you the moment you cross. From your perspective, nothing seems dramatically different, aside from the spaghettification in progress. But for any observer outside the black hole, your fate is sealed and your image would freeze. Due to extreme gravitational time dilation, as you approach the event horizon, time for you would appear to slow down from the perspective of an outside observer. The light you emit would become increasingly redshifted, moving towards longer, redder wavelengths, eventually fading to invisibility. From the outside, you would appear to slow down, freeze at the event horizon, and then disappear from view. From your perspective, however, time would continue normally. You'd fall inexorably towards the singularity. The light from the entire universe would be compressed into a tiny, intensely bright spot directly above you, a distorted view of all existence. Below you, absolute darkness. And here's where our understanding of physics truly breaks down. What lies inside the event horizon? Our current theories, specifically general relativity, predict that all the mass collapses into a singularity, an infinitely dense, infinitely small point. But general relativity does not include quantum mechanics, and at the singularity, gravity becomes so strong that quantum effects must become important. We don't have a theory that successfully combines general relativity and quantum mechanics, a theory of quantum gravity. This means we literally do not know what happens at the singularity. It's a point where physics itself throws up its hands and says, we don't know. Could there be something else? Exotic forms of matter, a bounce back out, another universe. These are wildly speculative ideas, but they highlight the profound limits of our current scientific knowledge within the event horizon. Now, a brief, slightly less gruesome thought experiment. What about falling into a supermassive black hole? These are the behemoths at the center of galaxies, millions or even billions of times the mass of our sun. Ironically, falling into one of these would be a far less painful experience, at least initially. Because their mass is so immense, their event horizons are much larger. The tidal forces at the event horizon of a supermassive black hole are much weaker than for a stellar mass black hole. Imagine SSR, the 4 million solar mass black hole at the center of our galaxy. Its event horizon is about 24 million kilometers across, roughly 17 times the diameter of our sun. If you fell into SSR A, you could cross the event horizon without even noticing it, without being immediately spaghettified. You'd pass this point of no return, perfectly intact. You'd have a few minutes, maybe an hour or two, to ponder your predicament before the tidal forces closer to the singularity eventually claimed you. But from an outside observer's perspective, you would still appear to freeze and vanish at the horizon. This distinction between stellar mass and supermassive black holes is crucial. It shows that black hole is a spectrum, and the experience of encountering them varies wildly with their size. But the ultimate fate is the same. Once you cross the event horizon, you are disconnected from the observable universe. Your future is inexorably linked to the singularity, and your journey ends in the unknown, in a realm where time itself might cease to have meaning, or perhaps flows only in one direction, inwards. Spaghettification and the event horizon are not just theoretical constructs. They are direct, inescapable consequences of Einstein's theory of general relativity, confirmed by a wealth of astronomical observations. They are a powerful reminder of how gravity, when concentrated to such an extreme, can warp space-time, dissolve matter, and utterly redefine our most fundamental intuitions about space, time, and existence. They are the ultimate cosmic oddity, a portal to where the known laws of physics reach their breaking point. And speaking of supermassive black holes, these cosmic behemoths aren't just destroyers, they are also galactic architects, a topic we'll dive into next. Now, let's zoom out, far beyond individual stars, and look at the very heart of galaxies themselves. Because at the center of nearly every large galaxy, including our own Milky Way, lurks an entirely different class of black hole, the supermassive black hole. And these cosmic giants aren't just destructive forces, they are, in a profound and unexpected way, the architects of galaxies. Imagine something with the mass of millions, even billions of suns, compressed into a region no larger than our solar system. That's a supermassive black hole. Our own Milky Way is home to Sagittarius, a CSJ-A, a supermassive black hole with a mass of about 4 million suns. Other galaxies harbor even larger ones, like the one in Messier 87, which is over 6.5 billion times the mass of the Sun. The existence of these colossal black holes presents a fascinating puzzle. How do they get so big? Unlike stellar mass black holes, which form from the collapse of individual stars, supermassive black holes require a different explanation. The leading theories suggest a couple of possibilities. They might start as seed black holes, perhaps formed from the collapse of the very first, most massive stars in the early universe, or even from the direct collapse of massive gas clouds. Once formed, they grow by two primary mechanisms, accreting gas and dust from their surroundings, relentlessly feasting on matter that falls into their gravitational well, and through mergers with other black holes, particularly during galaxy collisions. But here's the counterintuitive part. These destructive giants don't just sit there. They are intimately, dynamically linked to the evolution of their host galaxies. For a long time, astronomers thought of galaxies and their central black holes as separate entities. But according to a wealth of observational data gathered over the last few decades, particularly from X-ray observatories like Chandra and optical telescopes like Hubble, we now understand that galaxies and their supermassive black holes co-evolve. The growth of one seems intrinsically tied to the growth of the other. How? When a supermassive black hole is actively feeding, pulling in vast amounts of gas and dust, it forms a bright, energetic accretion disk around it. This disk heats up to incredible temperatures, emitting powerful radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Sometimes, these active black holes also launch powerful jets of plasma outwards at nearly the speed of light, extending far beyond the galaxy itself. When a supermassive black hole is in this active, luminous phase, we call it an active galactic nucleus, or AGN. AGNs are some of the brightest objects in the universe. So bright, they can outshine the entire galaxy they reside in. Quasars, which we'll discuss in more detail later, are a particularly luminous type of AGN. These colossal outflows of energy, both radiation and powerful winds or jets, can have a profound impact on the surrounding galaxy. Imagine this. As the black hole feeds and unleashes its power, the energy and radiation it emits can actually heat up and push away the gas in the galaxy. This might sound destructive, but it's a crucial regulatory mechanism. By pushing away the gas, the black hole effectively shuts down star formation in certain regions. No gas means no new stars. This process, often called feedback, is thought to be essential for preventing galaxies from growing too large and for explaining the observed properties of galaxies today, such as why massive galaxies often have old red stellar populations and less ongoing star formation. The black hole acts like a galactic thermostat, regulating the galaxy's growth. It's an astonishing concept. The most powerful gravitational engines in the universe don't just destroy, they control and shape. They're not just passive residents, they are active participants in the cosmic ballet of galaxy formation and evolution. Without them, galaxies might look very different, or not even exist in their current forms. The observation that the mass of a supermassive black hole is often tightly correlated with the properties of its host galaxy's bulge, the central, roughly spherical component, is compelling evidence for this co-evolution. According to numerous studies, including those using data from the Gemini and Keck observatories, there's a strong correlation between black hole mass and galaxy stellar velocity dispersion, a measure of how fast stars are moving in the galaxy's bulge. This strongly implies a fundamental, regulatory connection. So, the next time you think of a black hole, move beyond the simplistic vacuum cleaner image. Think of it as a cosmic architect, a powerful engine of feedback that, through its destructive capabilities, ultimately sculpts and balances the majestic structures we call galaxies. From the quiet behemoth at the heart of our Milky Way to the roaring quasars at the dawn of time, supermassive black holes are not just cosmic oddities. They are foundational elements of the universe's grand design, intimately connected to everything we see. And speaking of the subtle ways massive objects influence light, next we'll explore how these cosmic giants can literally bend light, creating mirages and revealing the invisible gravitational lensing. We've just seen how supermassive black holes act as galactic architects, shaping the evolution of entire star systems. Their gravity is immense, but its effects can be subtle yet profound, even on something as fundamental as light. And that brings us to our next cosmic oddity, one that truly allows us to see the invisible and peer into the universe's most distant corners, gravitational lensing. When you think of a lens, you probably picture a glass object, like an eyeglasses or a telescope, that bends light to magnify or focus an image. But in space, there are no giant pieces of glass floating around. Yet, the universe has its own, much more powerful and utterly bizarre lenses, massive objects. The concept dates back to Albert Einstein's theory of general relativity, published in 1915. Einstein proposed that mass warps the fabric of space-time itself. And if space-time is warped, then light, which always travels along the straightest possible path in space-time, will appear to follow a curved path when passing near a massive object. It's not gravity directly pulling on light in the Newtonian sense. It's light following the curves in space-time created by mass. Imagine stretching a rubber sheet taut. Place a bowling ball in the center. It creates a dip. Now roll a marble across the sheet. It won't go in a straight line, it will curve around the bowling ball. That bowling ball is a massive galaxy or cluster of galaxies, and the marble is a beam of light. So, how do we observe this? When a massive object, a foreground galaxy, a cluster of galaxies, or even a single star happens to lie directly between us and a more distant background light source, its gravity acts like a cosmic lens. The light from the distant object gets bent and focused around the foreground mass before reaching our telescopes. This bending can manifest in several ways. First, it can magnify the distant object. Just like a magnifying glass, the gravitational lens can make faint, incredibly distant galaxies appear brighter and larger than they would otherwise. This is incredibly powerful because it allows us to see some of the very first galaxies that formed in the early universe. Galaxies that would be far too dim to detect without this cosmic assist. According to observations from the Hubble Space Telescope, many of the most distant and earliest galaxies ever discovered were found using gravitational lensing. Second, it can distort the image of the background object. Instead of seeing a single, clear image of a distant galaxy, we might see it stretched into long, luminous arcs, or even multiple images of the same galaxy, ringing around the foreground lens. These distorted images are some of the most beautiful and bizarre sights captured by telescopes. Think of looking through a wavy glass panel. The image behind it is stretched and warped. A famous example is the Einstein ring, where the alignment is so perfect that the background source appears as a complete circle around the foreground lens. Third, and perhaps most profoundly, gravitational lensing is one of our most powerful tools for detecting and mapping dark matter. We talked about dark matter earlier, the invisible scaffolding of the universe. It doesn't emit or absorb light, so we can't see it directly. But it does have mass, and therefore, it does exert gravity, and if it has gravity, it bends light. By carefully observing the lensing effects around galaxy clusters, astronomers can measure the total mass present, including the invisible dark matter. When we look at how light is bent around a cluster, we see far more gravitational bending than can be accounted for by the visible stars and gas alone. This discrepancy is direct, compelling evidence for the presence of vast quantities of dark matter, whose gravity is doing the extra bending. According to groundbreaking research on the Bullet Cluster, a galaxy cluster where two smaller clusters have collided, gravitational lensing clearly showed that the bulk of the mass, dark matter, had passed straight through, while the visible gas, ordinary matter, had slowed down, providing some of the strongest evidence for dark matter's existence. There are different types of gravitational lensing. Strong lensing is what creates those dramatic arcs and multiple images. It happens when there's a very massive foreground object and a very precise alignment. Weak lensing is more subtle. It causes slight, statistical distortions in the shapes of many distant galaxies around a foreground cluster. By analyzing these tiny distortions, astronomers can create detailed maps of the dark matter distribution on even larger scales. And then there's microlensing, which we discussed in the context of rogue planets. That's when a single star or planet passes in front of a distant star, causing a brief brightening and magnification. Gravitational lensing isn't just a fascinating parlor trick of gravity, it's an indispensable tool in modern cosmology. It allows us to study the earliest and most distant galaxies, providing insights into the universe's formative years. It gives us our most concrete evidence for dark matter and helps us map its distribution, unlocking one of the universe's greatest mysteries. It allows us to weigh galaxy clusters, measure the expansion rate of the universe, and even search for elusive objects like isolated black holes. So, the next time you see one of those stunning images from the Hubble or James Webb Space Telescopes showing distorted arcs of light around a galaxy cluster, remember, you're not just seeing beautiful cosmic art. You're witnessing space-time itself being warped, light being bent by invisible mass, and astronomers using Einstein's genius to see the unseeable, pushing the boundaries of what we can discover in the vast, strange cosmos. And speaking of directly observing the fabric of space-time, our next oddity allows us to hear the universe's most violent events, gravitational waves. We've explored how massive objects bend light through gravitational lensing, allowing us to see the invisible hand of dark matter and peer into the early universe. That bending of light is a profound consequence of Einstein's general relativity, showing us that space-time isn't a static, unchanging backdrop, but a dynamic, malleable fabric. Now, let's take that concept one step further. What if this fabric of space-time isn't just bent by mass, but can actually ripple and vibrate? What if the most violent events in the universe send tremors through the very geometry of reality itself? Welcome to the world of gravitational waves, ripples in the fabric of space-time. Just as an accelerating electric charge produces electromagnetic waves, like light, radio waves, X-rays, an accelerating mass produces gravitational waves. This was another astonishing prediction of Einstein's general relativity in 1916. But unlike electromagnetic waves, which are ripples in the electromagnetic field, gravitational waves are ripples in space-time itself. They literally stretch and squeeze space-time as they pass by. Imagine a calm pond. Dropping a pebble creates ripples that spread outwards. Now imagine the cosmos as a vast, calm sea of space-time. Cataclysmic events, like two black holes spiraling into each other and merging, or two neutron stars colliding, are the pebbles. They send out ripples, gravitational waves, that travel across the universe at the speed of light. For decades, gravitational waves remained purely theoretical. They were incredibly difficult to detect, because the effect they have on space-time is minuscule. Even the most powerful cosmic events produce waves that, by the time they reach Earth, stretch and squeeze us by less than the diameter of an atomic nucleus. It's an effect so tiny, it seemed almost impossible to measure. But in 2015, after decades of painstaking scientific effort and technological innovation, something extraordinary happened. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, made history. It directly detected gravitational waves for the very first time. How did they do it? Imagine two giant L-shaped detectors, one in Livingston, Louisiana, and one in Hanford, Washington. Each arm of the LIL is 4 kilometers, 2.5 miles long, forming a colossal interferometer. A laser beam is split and sent down each arm, bouncing off mirrors at the end and returning to a detector. If a gravitational wave passes through, it will momentarily stretch one arm of the LIL while squeezing the other, changing the path length of the laser beams by an infinitesimal amount. This tiny difference in path length, smaller than 1,000th the width of a proton, can be detected as a change in the interference pattern of the light. The signal detected by LIGO in 2015, dubbed GW150914, was the unmistakable chirp of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging roughly 1.3 billion light-years away. It was a moment of profound scientific revelation, directly confirming a century-old prediction of Einstein and opening up an entirely new window onto the universe. The discovery of gravitational waves marked the birth of gravitational wave astronomy. For millennia, humanity has observed the universe using electromagnetic radiation, light, radio waves, X-rays, gamma rays. This is like seeing. Gravitational waves are like hearing. They allow us to hear the most violent, cataclysmic events in the universe that are otherwise invisible to traditional telescopes. We can now detect events where light is often obscured or simply not produced, like the merger of two black holes. Since that first detection, LIGO, along with its European counterpart Virgo, and now Kagra in Japan, have detected dozens of these events. Most are from merging stellar mass black holes, but as we discussed in the context of gamma-ray bursts, we've also detected the collision of two neutron stars, GW70817, which was followed by a short GRB and a kilonova. This was a monumental event in multi-messenger astronomy, combining both gravitational wave and electromagnetic observations to paint a complete picture of a cosmic catastrophe. What do gravitational waves tell us? They've confirmed that black holes are real and that they come in a range of sizes. They've allowed us to directly observe the mergers of black holes and neutron stars, processes that were once purely theoretical. They offer a way to probe the internal structure of neutron stars, something still not fully understood. And they hold the potential to reveal even more exotic phenomena, like the echoes of the Big Bang itself, or perhaps even the collisions of supermassive black holes at the centers of galaxies, which would produce much lower frequency. Gravitational waves are a testament to the power of human ingenuity and our relentless quest to understand the universe. They've revealed the universe to be even more dynamic, more violent, and more awe-inspiring than we ever imagined. They've shown us that space-time isn't just a passive stage, it's an active participant, vibrating and echoing with the most extreme events. They are a profound cosmic oddity, a new sense through which we can perceive the cosmos, and they promise to unlock even deeper mysteries of reality itself. And speaking of space-time and its strange properties, our next topic delves into an even more mind-bending, yet theoretical, possibility: wormholes. We've just celebrated the incredible discovery of gravitational waves, ripples in the fabric of space-time, proving that space and time are not just a static stage, but a dynamic, vibrating entity. This flexibility of space-time, a cornerstone of Einstein's general relativity, opens up some truly mind-bending theoretical possibilities that push the boundaries of what we might consider real in the universe. And none are more captivating or more deeply ingrained in science fiction than the idea of wormholes, hypothetical tunnels through space-time that could offer shortcuts across vast cosmic distances. Imagine the universe as a flat sheet of paper. If you want to get from one point to another, you draw a line across the sheet. That's the conventional way to travel, straight through space, taking a very, very long time. But what if you could fold that paper? If you fold it so that the two distant points touch, you could then punch a hole through both layers, creating a much shorter path. That's the intuitive analogy for a wormhole, a shortcut through the universe, connecting two widely separated regions of space-time. Mathematically, wormholes are solutions to Einstein's field equations of general relativity, just like black holes. In 1935, Einstein and Nathan Rosen explored the idea of a bridge, connecting two different regions of space-time, or even two different universes. This early concept was known as the Einstein-Rosen bridge, and it essentially described a connection between a black hole and a white hole, a theoretical object that acts as a black hole in reverse, spouting matter instead of consuming it. However, these early wormhole solutions were highly unstable and, crucially, non-traversable. If you tried to pass through one, it would snap shut faster than anything could cross it. It was a mathematical curiosity, not a pathway. The idea of traversable wormholes, ones that you could actually pass through, gained serious theoretical traction in the late 1980s, thanks to physicist Kip Thorne and his colleagues. They found that for a wormhole to be stable and traversable, it would require something truly exotic matter. What is exotic matter? It's not just dark matter or antimatter. Exotic matter is material that possesses negative energy, density, or, equivalently, negative mass. it would have anti-gravitational properties. Instead of pulling things in, it would push things away. Imagine a material that, instead of adding weight to a scale, made the scale read less than nothing. Why is this needed? To keep the throat of the wormhole open and prevent it from collapsing under its own gravity, you need a powerful repulsive force. Negative energy density would provide that outward pressure, propping open the space-time tunnel. According to Thorne's research, exotic matter with this property is the fundamental requirement for a stable, traversable wormhole. The problem, of course, is that we have never observed exotic matter with negative energy density. It's theoretically possible under some interpretations of quantum mechanics, like the Casimir effect, which shows regions of negative energy density can exist on microscopic scales. But to create and sustain a wormhole large enough for a spaceship, that would require vast quantities of exotic matter on a scale we cannot fathom. So, while mathematically possible, the physical requirements for wormholes currently make them seem like a distant dream, if not outright fantasy. But the implications of wormholes, if they were possible, are mind-bending. First, interstellar and intergalactic travel. A wormhole could hypothetically connect our solar system to a distant galaxy, reducing a journey of millions of light-years to mere meters. This would revolutionize our understanding of distance and accessibility in the universe. Second, and far more problematic, is the issue of time travel. If you could construct a wormhole and then somehow move one of its mouths at relativistic speeds, it could theoretically connect different points in time, allowing for travel into the past. This immediately runs into paradoxes, like the grandfather paradox. What if you go back and prevent your own existence? This is why most physicists are highly skeptical of time travel to the past, viewing it as fundamentally incompatible with the known laws of physics and causality. The universe seems to have safeguards against such paradoxes. So, where do we stand on wormholes? They remain firmly in the realm of theoretical physics and speculation. There is no observational evidence for their existence. No one has ever seen a wormhole or anything that could be interpreted as one. Yet, they continue to be a fertile ground for physicists exploring the boundaries of general relativity and quantum gravity. They force us to ask fundamental questions about the nature of space-time. Is it truly connected in such ways? Are there hidden shortcuts? Wormholes are a profound example of how scientific exploration pushes not just the boundaries of what we observe, but what we can conceive. They are a testament to the fact that mathematical consistency can lead to concepts that challenge our deepest intuitions about reality. Even if traversable wormholes remain forever out of reach, their theoretical possibility expands our minds, allowing us to contemplate a universe far stranger, far more interconnected, and far more complex than the one we perceive directly. They are a powerful cosmic oddity, a bridge between scientific rigor and the wildest dreams of science fiction. And speaking of things that are profoundly hidden and challenge our perceptions of the universe, next we delve into the most pervasive and elusive oddity of all, dark matter. Let's pivot to a cosmic oddity that is not theoretical at all, but profoundly real and yet remains almost entirely invisible to us. It's one of the universe's greatest mysteries, and it acts as the invisible scaffolding upon which galaxies are built, dark matter. Imagine looking at a magnificent skyscraper. You see the glass, the steel, the lights, all the visible components. But you know that beneath all that, hidden within the walls and foundations, there's a colossal amount of concrete, rebar, and infrastructure you can't see, which gives the building its structure and strength. The visible parts are only a small fraction of what's truly there. In a cosmic sense, that hidden infrastructure is dark matter. For decades, astronomers have observed phenomena that simply cannot be explained by the visible matter in the universe, the stars, gas, and dust that make up everything we can see and interact with. Something else, something invisible, must be exerting a powerful gravitational influence. The story of dark matter really began in the 1930s, with astronomer Fritz Zwicky, who was studying the Coma cluster of galaxies. He observed that the galaxies in the cluster were moving far too fast to be held together by the gravity of the visible matter alone. If there wasn't extra, unseen mass, the cluster should have flown apart long ago. Zwicky famously coined the term dark matter, or Dunkelmaterie in German, to account for this missing mass. His findings were largely dismissed for decades, deemed too radical. But the evidence began to mount in the 1970s. spearheaded by astronomer Vera Rubin and her colleagues, who were studying the rotation of spiral galaxies. Imagine our solar system. Planets further from the Sun orbit more slowly. This is because most of the mass is concentrated at the center. You would expect the same for a galaxy. Stars further from the galactic center should orbit more slowly than those closer in. However, Rubin and her team found something astonishing. Stars on the outskirts of spiral galaxies were orbiting just as fast, or even faster than stars closer to the center. It was like watching a merry-go-round, where the outer horses were spinning at the same speed as the inner ones, defying the laws of physics if all the mass was visible. This could only mean one thing. There had to be a huge, invisible halo of mass surrounding the visible galaxy, extending far beyond the stars and gas, providing the extra gravitational pull to keep those outer stars moving so fast without flying off into space. This phenomenon is known as galactic rotation curves, and it's one of the most compelling pieces of evidence for dark matter. Then came gravitational lensing, which we just discussed. Remember how massive objects bend space-time, distorting light from background galaxies? When astronomers analyze the gravitational lensing effects around galaxy clusters, they find that the amount of bending is far greater than what the visible galaxies and hot gas in the cluster can account for. The only way to explain this extra bending is if there's a huge reservoir of invisible mass. The Bullet cluster, for instance, a collision of two galaxy clusters, provided definitive visual proof. The visible gas was separated from the gravitational lensing effect, showing that the bulk of the mass, dark matter, had passed right through, independent of the ordinary matter. Other lines of evidence include the cosmic microwave background, CMB, the afterglow of the Big Bang, the subtle temperature fluctuations in the CMB, observed by missions like COB, WMAP, and Planck, can only be explained if dark matter was present in the early universe, providing the gravitational seeds for galaxies and large-scale structures to form. Without dark matter, the universe would be much smoother and less structured. So, the evidence for dark matter is overwhelming and comes from multiple, independent observations across cosmic scales. It's not just a hypothesis, it's a necessity to explain the universe as we observe it. But here's the kicker. We still don't know what it is. Why can't we see it? Because dark matter doesn't interact with light, or with ordinary matter, in any way we currently understand, except through gravity. It doesn't absorb, emit, or reflect photons. This is why it's dark. It just passes right through us, through our planet, through stars, without a trace. It's like a ghostly presence, everywhere but nowhere. What are the leading candidates for dark matter's identity? The most popular candidates are weakly interacting massive particles, or WIMPs. These would be new, as yet undiscovered elementary particles that are much heavier than protons and neutrons, but interact only very weakly with ordinary matter, hence weakly interacting. Billions of WIMPs could be passing through your body right now, and you'd never know. Particle physicists are actively searching for WIMPs in underground laboratories, hoping to detect a rare interaction as a WIMP collides with an atomic nucleus. Another candidate is the axion, a much lighter hypothetical particle that could also explain some cosmic anomalies. Other, more exotic theories involve sterile neutrinos, or even primordial black holes formed in the very early universe, before stars, that are not too large or too small to be ruled out. However, ordinary matter, the stuff we are made of, protons, neutrons, electrons, accounts for only about 5% of the total mass energy of the universe. Dark matter makes up about 27%. That means about 5 times more stuff exists in the universe than all the stars, galaxies, and planets we can see combined. This is a profound cosmic oddity. We live in a universe dominated by something we cannot see, cannot touch, and cannot directly identify. It shapes galaxies, sculpts the cosmic web, and yet remains stubbornly hidden. The quest to identify dark matter is one of the most important scientific endeavors of our time, a testament to the fact that even with all our advanced instruments, the universe still holds vast, fundamental secrets. And speaking of secrets and discrepancies, next we'll delve into a specific puzzle related to dark matter, the missing satellites problem.